This video will serve as an introduction to equilibrium and reversible reactions. So to start with the reversible reaction, in order to have equilibrium, you need a reversible reaction. So all the reactions we've dealt with up until now were considered forward-facing reactions, meaning they drove to products, and that was it. A reversible reaction is one where the reactants become products by breaking the reactant bonds and making product bonds. But as products are made, there's enough energy to make it reversible where you can break the product bonds and make new reactant bonds. So essentially what that means is the reaction doesn't stop when all the limiting reactant runs out. The reaction stops at some arbitrary time where the rate at which I'm making product equals the rate at which the product is breaking back down to the reactant. So at equilibrium, I have both reactant and product. And the main thing about this unit is mathematically, everything we've seen with reactions and stoichiometry is going to be very different for reversible reactions since there isn't a limiting reactant basically determining when the reaction stops. So a couple things about equilibrium. I think of a really good image of chemical equilibrium, or a good analogy to use, is like running on a treadmill, which is awful, but essentially you reach equilibrium on a treadmill when your rate of forward motion equals the rate at which the belt is moving backwards, right? You're not really going anywhere, but you're at equilibrium with the belt, and that's what a chemical equilibrium is also. It's when the rate of change of the reactants becoming products equals the rate of change of which the products are becoming the reactants. Okay, so the change is the same both directions. We consider it a very dynamic process. If you thought about running on a treadmill, you wouldn't think of it as very static. You're not going anywhere, right? You're not getting anywhere. But it's very dynamic, and same with chemical equilibrium. If you looked at a system at equilibrium, it looks really boring. Nothing's happening. But dynamically, bonds are being broken and formed constantly. It's just that there's no macroscopic change because the rate at which things are being broken and formed equals the rate at which the reverse is also occurring. Okay, so the biggest thing about equilibrium is it's when the rate of change is equal, not when I have equal amounts. Okay. And just realize, just like a treadmill, that equilibrium is a very small and fine balance. If for some reason your rate going forward becomes less than the rate of the belt, right, catastrophe occurs. So same with chemical equilibrium. We can definitely stress it and shift it, but that fine motion or that fine kind of balance exists. So you had to graph it in your simulation with equilibrium. And here are the main types of graphs that we usually see with equilibrium. Two of them are concentration, one of them is rate. Okay, they emphasize the main point at equilibrium, which is the idea that equilibrium does not mean equal amounts. Equilibrium means equal rates. Okay, so on the two graphs, we're graphing amount, which here we're depicting as concentration. At equilibrium, I don't have equal concentrations. I just have concentrations that aren't changing. So you know a substance at equilibrium, if you look at it and you go, oh, it turned pink and it sat there. So your concentrations are no longer changing. The other graph, the rate graph, we do have an intersection of the two lines because what equilibrium means is the rate forward is the same as the rate backwards. Okay, so those are the main two graphs we see, and you do want to make sure you know the difference between them. So mathematically, here's what we do with equilibrium. You will be creating your own equation for equilibrium. You'll be creating what's called a K expression. And what a K expression is an expression where K equals something. K is the equilibrium constant because, again, it's not about limiting reactant. It's about some moment in time where the rates are equal. This point in time is different for every reversible process. Okay, so we've created something called K, which is the equilibrium constant. It's the constant for equilibrium mathematical expressions where it's the ratio for when you get to equilibrium, how much product do I have compared to how much reactant I have. Whatever that ratio is, that's my constant. Okay, so it's a weird idea of a constant that it's not just one number. It's a constant that's reaction dependent and temperature dependent. So if I change the temperature, the equilibrium shifts as well. So K equals, what you're going to see on this slide here are these brackets. Brackets mean molarity, right, or moles per liter. So if I put a substance inside this bracket, that means the concentration of carbon dioxide. So the equilibrium constant, or KEQ, equals the concentration of a substance. And then it also equals that substance raised to a power of its coefficient. So if within a chemical reaction I had carbon dioxide and had a 2 as a coefficient, I would square this number, or that kind of factor. K expressions are always products divided by reactants. So products are on top and reactants are on bottom. So let's try some of these out. So there's a couple equations on the slide. The first one is H2 plus I2 equals HI. So the K then, HI, concentration of that, is going to go on top. And then on bottom will be the 2 other factors. And then I'll raise HI to the power of its coefficient. H2 and I2 have no coefficients on them, so they don't have a power. One other thing people tend to make mistakes on is right here. This is multiply. So I'm multiplying those 2 factors together, concentration of H2 times the concentration of I2, not adding them. In the chemical equation, I'm adding them. In the equilibrium expression, I'm multiplying them. Okay. The other example on this screen, again, it's products over reactants. Now I have 2 products instead of 2 reactants. So I'm multiplying 2 substances on top. I'm going to raise PCl3 to its coefficient. And then the reactant will go on the bottom. And again, that has a coefficient. So I'm going to raise it to its power. So this is setting up the math. Eventually we're going to plug into this, like I'll give you a KEQ and some of the numbers and you'll solve for the other one, or I'll give you some of the numbers and you can solve for KEQ. The one thing we can think about this mathematically right now is the ratio and what K can tell us. Okay, so if we had a situation where K was greater than 1, the only way to get a K of greater than 1 is to have this product be bigger than these reactants. So K greater than 1, we usually say is product favored because the products are on top. And so to get a K of greater than 1, we have to have a lot of products. If, on the other hand, K is less than 1, we usually call that reactant favored because the only way to get that is to have the denominator big, or the reactant number big. And to get the reactant number big, we have to favor the production of reactants. Now, the only other thing, just nomenclature-wise or naming-wise, when we see a reversible reaction like this, standard practice is to say that the reaction proceeding in this direction is the forward-facing reaction, and these are the reactants, and these are the products. If instead I'm proceeding this way, where HI is becoming H2 and I2, that is the reverse reaction, still called products, still called reactants though. So whatever's on the left are the reactants, whatever's on the right are the products, regardless of what I put in. So if I had this particular reaction and this particular K expression and put in a whole bunch of HI, HI is still the product. And essentially the reverse reaction would be favored at the beginning until the rate slowed down. So that's just standard practice, otherwise the K expression is wrong. So just some generic things again about equilibrium. I've said some of these, but this is super important. Not every reaction is reversible, right? We need enough energy for the products to break and be able to remake the reactants. You know you're at equilibrium when you have equal rate of change, not equal amounts of concentration. And do realize that rate is a flexible concept in that at the beginning of a reaction, the rate forward might be really big and then it will slow down, and the rate reverse might be really small and then it speeds up until they get to that point where they're equal. So rates are variable and change a lot, but equilibrium means when they're equal. Okay. The other key part here is that K again. K is a constant. It's a ratio of products on top, reactants on the bottom. K is unique for every process, but it is temperature dependent, meaning it's not like if you know, like, this reaction's K is always 2. Well, no, it will have a temperature factor as well, and it will be different at a different temperature, okay? K is independent of concentration, though, meaning if I change, like, one of these concentrations, the other ones will adjust accordingly to keep K the same value. K is a constant. The other thing about K is it's not affected by a catalyst. So K is affected by temperature, and K is affected by the reaction, like what reaction you're doing. But a catalyst will speed up the process, but it'll speed it up in both directions. So the forward reaction will happen faster and the reverse reaction will happen faster. Thus, the equilibrium position will be in the same spot. The only other weird thing about equilibrium expressions is that they are state dependent, meaning the things that affect K are those things that are either gas in terms of state of matter or aqueous. So within a chemical reaction, if you have a solid or you have a liquid, those are not part of the equilibrium expression in terms of the value of the K. So this particular reaction on the screen of the decomposition of calcium carbonate, if we follow the same rules I've already taught you, products over reactants, the K would look like the top part, right? Carbon dioxide and calcium oxide on top, calcium carbonate on the bottom, no coefficients, so no powers. Now, because 2 of those substances are solids, and solids are not part of the equilibrium expression, they just drop out. So the actual K expression for this guy is just the concentration of carbon dioxide. That's the only thing that is affecting the value for K. So to see some practical examples of that, here are 3 of them I'll run through. So for number 1, products over reactants, again, using the rules we had before, we'd have 2 factors on top and 1 on bottom. But now seeing that solids and liquids aren't included in the expression, that means my KEQ will not equal the concentration of KNO2 because that's a solid. So it's going to equal just O2 on top, no power because no coefficient, and KNO3 on the bottom solid. So I don't need to include it. So KEQ is just O2 for number 1. For number 2 then, KEQ equals products over reactants. So I have that sodium sulfate as one of my products, and then liquid water as the other one. And since liquid water is a liquid, I wouldn't include it as part of my expression. And then in terms of reactants, I have H2SO4, and I have sodium hydroxide. That one has a coefficient, so I'm going to square it. And again, remember right here, this is multiply. This is not add. So I multiply my factors within my K expression. The last one then, if you look at it, all the substances are gases, which means all of them affect the value of my equilibrium. So all of them would be part of my expression. That's it for your introductory to equilibrium. Realize the next step is to do the math. Most common issues with the math is the multiply, this, having a power in general and forgetting about it. And then knowing that it's always products over reactants. So we'll practice writing some of these expressions, and then our next step will be to math them. Have a nice night.